Tapi as we can see here, under this loading, we can expect that this bar ni dia akan deform under this load. Mungkin dia akan memanjang ataupun dia akan compress kan. Tapi in one direction sahaja, which is dalam arah X sahaja. Dia tak akan jadi macam gini. Kan?
Betul.
That means kalau dia ada pempanjangan, this bar ni dia akan elongate. Mungkin point C ni dia akan elongate sampai ke sini. Tapi kalau kita tengok dekat sini, pada point B tu dia punya load lagi besar kan. So mungkin dia akan ada under this load, mungkin dia ada menyebabkan compression pada point number 1 ni, atau point element number 1 ataupun bar number 1. And then mungkin ada pemanjangan juga pada C, tapi not that very much.
Hello
So
everyone,
all of
welcome
them
to
in term of the, kita panggil dia deformation ataupun displacement. Only
Finite Elements
in
solve
X direction sahaja.
a similar approach
So
can
in
be
this
applied.
case, when we expect that the elongation, deformation only in X direction, even though dia punya bar dia adalah in 3D, kan, in 3D, tapi deformation in one direction only, so kita boleh simplifykan model ni dengan apa ni, dengan assumption kita, problem ni instead of 3D problem, we can assume it as a 1D problem. Tapi in detail lah, kalau kita tengok in detail, when we pull something, dia bukan sahaja memanjang, tapi some portion dia akan shrink kan, macam gitu kan, dia akan shrink. Tapi in term of the shrink ni, kita tak consider in this case. Kita assume that the shrinkage to the kita punya structure is very very small under this load. Is very very minimal. So this is just to give you an overview what kind of problem that we can consider it as 1D problems. Saya minta maaf sebab saya ada ulcer ni sikit dalam mulut, tak selesa sikit nak bercakap hari ni.
Boleh habis awal tak apa.
Alright, in term of objective, the objective of our very first topic on the finite elements model or methods here is to develop actually apa yang kita nak buat kat dalam kita punya kursus ni to look these finite elements methods dari sudut mathematics dia. And then bila kita dah ada kita dah faham mathematics dia, toward the end of our analysis, kita still solvekan engineering problem tu. Tapi sebelum kita dapat solution dia yang akhir tu, yang mana kita akan solvekan engineering problem, kita mesti solvekan mathematics dia tu dulu. So that's why the first objective here which is to develop system of linear equation. So nanti kita akan tengok how we can develop system of linear equation out of finite element method for 1D and 2D problems lah. 2D problem tu dalam topik-topik yang akan datang. So we start with 1D and then to apply finite element method for solving general problems involving bar structure with different support condition. Okay. Ini adalah keyword yang agak penting.
Support condition.
Okay, kalau boleh kamu highlight dia. Dalam finite elements, especially when we solve, kita gunakan finite element ni untuk solve a structural problem, then there will be several support conditions. Okay, support condition to our structure. So kita ada sebagai contoh. Tadi kita dah tengok fixed boundary condition. So satunya adalah fixed. Kita panggil fixed support conditions ataupun later on we call it as the boundary condition as well. Support or kalau kita tengok in the real case lah, dekat site ke, dekat depan kamu ke, kita tak kata dia sebagai, kalau kita apa tu a drill, then kita tightenkan some structure on the wall, kita tak cakap yang kita buat tu sebagai boundary condition, kan? Kita panggil dia support condition. Tapi in mathematics, kita panggil dia sebagai boundary condition. Okay. In mathematics tu, kita panggil dia sebagai boundary condition to the equation kita tu. So, yang pertama adalah fix. So, kalau fix, dia punya support condition ataupun boundary condition, biasanya kita tunjukkan, let's say this is our bar. So, ini you all kena faham ini. So, this is our structure. Then, we fix it on the wall. So, the fixed boundary condition is usually drawn macam gini. Ni macam ni. So this is what we call it as the fixed condition ataupun fixed support or boundary condition. Yang keduanya, we can have fixed roller. Kita okay, bolehlah fixed roller. Boleh ke fixed roller?
Tak pernah dengar.
Okay, fixed roller, it will be something like this. Assuming this is kita punya wall ataupun floor. Okay. And then this is our structure. Okay, ni kita punya structure. And then from the structure, okay, from the structure, it may be attached to something which will make it fixed. Okay, this is the structure that will make this another structure will, bila dia attach ke bila kita punya structure kita ni attach kepada support ni, benda ni dia akan jadi fix lah. Fix maksud dia tak boleh nak move, dia tak boleh nak rotate, kan? Macam kalau kamu ni lah, kalau kamu apa ni fitkan something on the wall, kamu cuba goyang-goyangkan dia tak boleh nak pergi ke mana-mana, kan? Dia duduk situ je. Macam kalau kamu gantung aircon, kalau ada aircon kat rumah, kalau ada kipas lah, dia punya dekat dia fit kepada ceiling je, kan? Kipas tu pusing, batang tu duduk kat situ je. Tu maksud dia fix. Tapi in this case, kita ada fix. These structures cannot move up and down, cannot rotate, but somehow it can slide. Ni dia ada roller. And this roller in this way, maksud dia boleh slide ataupun move up and down. Okay, so this is kita punya wall lah. Kita punya wall. Dia akan slide pada wall. Biasanya kita akan lukis macam gini lah kalau dalam contoh soalan pun. And then yang ni pun dia boleh apa ni? Kita boleh rotate lah dia punya boundaries dia. It can be in this position.
Takkan bersama diriku.
So in this case, our structure, okay, this structure can move to the right and to the left. Tapi dia tak boleh nak move up and down lah. Dia tak boleh rotate. And then number 3, okay, in terms of the support condition, we can have roller sahaja. Usually we call it as a pin roller. Pin roller. So kalau pin saja ataupun saya lukis pin dulu lah, pin. Tapi untuk case pin ni kita jarang consider untuk bar, tapi saya just list down je terus. So pin usually it will be drawn as shown here. So this is the symbol for pin. Sorry. So our structure is attached to the pin, something like this. So in the case where we use pin as our support condition, so the structures itself, kalau kita tengok kat sini, pin tu dia fix kepada wall. Maksud dia tak boleh to the left, to the right, up and down. Tapi sifat fizikal bagi pin ni, kita membenarkan dia to rotate, kan? Rotate to the left and to the right about this pinpoint dia dekat situ. And then we can have another number 4, pin roller. So in the case where we have pin roller, then our symbol that we use for the pin roller, which is as shown here. Kita ada pin, and then kita ada macam tayar ni, roller, and then our structure is attached to the pin. So in this pin roller support condition, the structures can rotate to the left and to the right about this point, and at the same time it can move to the left and to the right. So dia ada banyak sikit lah dia punya apa tu, darjah kebebasan dia, kan. Dia bebas bergerak ke kiri ke kanan, dan dia boleh bebas bergerak in rotation. So so this is the some of the support condition that we are gonna use in throughout of our finite element. Nanti you all will face this almost in every chapters except chapter number 7 and 8, which is when we discuss about heat transfer. From the chapter number 2 until number 6, you will see this type of support or boundary conditions are quite a lot. And dia ada lagi satu, which is symmetry boundary condition. Yang ni in some cases juga symmetry boundary condition. So in some cases where when the load of the structure, when the geometry of the structure they are symmetry between each other, then we can macam yang example dalam kita punya meeting sebelum ni, kan, instead of kita modelkan pipe yang T-junction pipe tu, instead of kita modelkan dia keseluruhan pipe, kita boleh ambil 1/4 saja, and then we apply symmetry boundary condition pada pipe tu. So similar, dekat sini kita ada symmetry support conditions or symmetry boundary conditions. So when our structure is in term of dia punya geometry is perfectly symmetry, the load is perfectly symmetry as well, and then dia punya support condition yang lain-lain pun dia symmetry, then kita boleh modelkan half of it ataupun quarter of the structures only, instead of kita modelkan keseluruhannya, and then we apply the symmetry support condition, which is on the symmetry punya plane we apply the fixed roller to represent the symmetry boundary condition. Sebagai contoh lah, sebab dia tak nampak kan. I will draw a bit here. Let's say I have a structure which is look like a house structure lah, lebih kurang lah, ataupun roof structure. Okay, geometrically the size, the dimensions lah, the dimension of this structure on the kalau kita tengok ni, geometri dia hampir sama kan. So we can take it half macam gitu. On the right hand side, geometrically exactly the same as on the left hand side. So sebelah sini lah maksud dia, sebelah kanan dengan sebelah kiri. And then kalau ada boundary condition, let's say kedua-duanya adalah fixed. Okay, and then in term of the loading, let's say kita ada loading. Loading pun sama. Let's say kita ada loading which is we have the distributions of the pressure which is exactly the same on the left and on the right. So boundary condition sama, geometry sama, loading sama. Then in this case kita tak perlu nak solvekan the whole structure ni. What we can do, we can take only half of it. Nak ambil yang sebelah kiri saja pun boleh, nak ambil sebelah kanan saja pun boleh. So apa yang berlaku nanti kalau kita ambil yang sebelah kanan je, instead of we solve 1, 2, 3, 4 element in our structure, ada banyak elemen kan, kita boleh modelkan dia 2 saja. Let's say element 3 and element 4 saja. Then we apply the same boundary condition. We apply the loading similar to the full structure lah. Tapi what will be happen ni dekat sini? Kalau kat sini dia bersambung, tapi kat sini apa berlaku dekat sini? Ni dekat sini ni. What will be happen here at this particular point? Takkan dia hanging? It is not going to be hanging because in physically in the real for the full structure ni dia attached to the other side. Alright, in that case we can since we considering this structure as a symmetry, then we can substitute what is happening here with the fixed roller. So saya pakai warna merah. So we can substitute it with pin roller type of boundary conditions. That mean bila fixed roller ni, kalau kita tengok kat sini apa yang berlaku under this load, potentially the roof will mungkin dia akan deform macam gitulah. Yeah. Mungkin dia akan deform macam gitu kan. So dia tak akan, sebab dia simetri, dia tak akan jadi macam gini. Dia tak akan jadi macam gitu. So bila dia simetri, dia akan deform uniformly juga, secara uniform juga. So that's why we allow the structure to move up and down. Tapi dia tak boleh pergi to the left and to the right. Boleh follow untuk introductions to boundary condition. Biasa saya tak sentuh pun pasal boundary condition awal-awal, tapi saya rasa it is better to understand the boundary condition before we go further and further lah. At least kamu kamu tahu kewujudan boundary condition ni lebih awal. Yang ni saya boleh share dekat ni lah, dekat kita punya group tu. Let me share with you. Alright. So next is ada apa-apa soalan tak setakat ni? Ke semua dah tinggal pergi makan dah? Dah makan belum semua?
Dah makan apa? Dah.
Alright. So, okay, saya proceed kat sini lah. Okay.
Dah.
Alright, now, okay, panjang lebar juga ni saya cerita ni yang support condition ni. So, our objective is to develop system of linear equation from our structure by using
Bersamamu
the concept of the
aku
finite element,
takkan
then
pergi.
considering the support condition as well. Tapi before we are able to deal with or set up the system of linear equation SLE, but we need to understand what is general loading that we are going to consider in our analysis later. Because as I mentioned, starting from this chapter number 2 until chapter number 6, we are using structural problems um, as our problems lah untuk kita understand finite element. Sebab kalau kita kalau kita guna fluid problem untuk kita fahamkan finite element, fluid tu dia lagi susah tau. Finite element ni saya rasa very easy lah. Kalau fluid, kita gunakan fluid sebagai kita punya problem, which is very hard to understand. Sebab dia punya boundary condition dia pelik sikit. Dia punya apa ni, untuk fluid.
Betul boleh kata tu betul.
Alright, SLE. Kita tengok SLE dulu. So, what form of system of linear equation that we are going to solve for solving structural problem? So, the system of linear equation that we are going to generate from finite element method, which is in the form of K, Q equal to F. So, sepanjang topik nombor 2 sampailah topik nombor 8, this is in general system of linear equation that we are going to generate adalah dalam bentuk KQ equal to F. Nanti sepanjang kita discuss, ini je yang kita nak hasilkan nanti. So, what is K? K is the matrix. K is the matrix that contains informations of the structural punya material and also structural punya geometry information. Dia ada disimpan dalam K. And F which is the vector which dealing with external load applied to our structure. And Q is the deformation of our structure that we are going to solve. Ini yang kita nak cari, Q. K kita boleh dapat. Let's say kita ada certain structure. Dia dah ada dimension dia, panjang, lebar, dia punya diameter. Kita tahu, then kita akan supply dia kepada K matrix. Dia punya material properties, modulus of elasticity. So, semua akan masuk ke sini. Saya tulislah area, length, and then material punya informations, modulus of elasticity. So kita akan supply dia dalam K matrix. F which is applied, which is refer to the applied force or external load yang dikenakan kepada kita punya structure. Then we supplied it to the F vector. So that's why under this subtopic 3.2 we discuss about this general loading condition. Untuk 1D bar problem, at least 3 type of general loading condition we may exist and will be considered in our course. The first one is called as the body force. Okay, body force given by F, which is the force that apply to our structure, everywhere to our structure. Actually, kalau kita tengok macam ini, kita tak jelas. What I can show to you, you can imagine that our structure, let's say in 3D. In 3D, let's say macam gitu dia punya structure dia. And then when the structure is in 3D, sini pun dia akan jadi macam gini lah roughly. Okay. When let's say I take a small portion of this structure, saya potong this part here. Okay, saya potong dia, and then I take it out. Saya timbang dia. So dia ada value of the weight, right? So this body force actually came from the weight of the structure itself. Kalau saya ambil small portion kat sini, dia ada body weight. Dia macam gini, kalau you nak imagine, let's say this is our body. Saya tak pandai nak lukis orang. Saya lukis orang, orang DT je. Right. So we can imagine body weight. If let's say I just chop my hand lah, chop out my hand, then saya timbang. So the hand itself, dia ada its own weight. Kaki, dia ada its own weight. Head, kan, dia ada its own weight. Itu yang kita panggil sebagai body weight. Tapi bila kita combine semua, kita ada total weight of the structure. So F, which is refer to the small portions of the weight came from from the small sections of the structure itself. So body weight ni weight yang terkandung dalam structure tu itself. And then number 2, we have traction force. So given by T. T refer to the traction force. Dia ada dalam slide sebelah ni, tapi saya just explain dulu. Ini kita panggil traction. And this traction force, which is the force that acting on the surface. So dia acting on the surface of our structure. Maksudnya pada permukaan luar structure tu. Dia boleh terhasil daripada geseran, viscosity. Kalau kita imagine piston dalam enjin ni kan. So dia selalu bergerak atas ke bawah. Dan di antara piston dan metal dengan dia punya rod pun metal, kita letakkan apa tu? Pelincir kan, pelincir. So this pelincir actually give some traction for resistance to the structure to move up and down. So kalau that's one example of the traction force. Then we can imagine as well, let's say I have a wing, and then this wing, we blow air around the wing. Okay. Then depending on which type of fluid that we use, whether it's air or some type of gas. And the friction between the air and the solid surface, dia hasilkan friction kan. So the friction between air and the solid surface also
Traction force.
So ada dua. First is the FBD, body boleh, and then traction force. And then the third one, kita tengok kat sini, we have a force that apply to nampak apa? Saya tu agak gagal. We have a force that apply to a specific points to our structure. Pada point number 1, and then there's another specific point, and we have the force that apply to specific point. within our structure. So this type of force, we call it as the point load. So this type of force, itu dekat sini, dikenali sebagai point load. And it is represented by P in this action in this figure. So we have three types of forces, and the explanations you can find it here in this slide. So this is what I mentioned to you just now. The force is distributed per unit volume when we're talking about the body force. That's why I draw the drawing just now in 3D. And then for the tractions, which is force per unit length, for example, friction, viscous, surface shear. And for the point load, which is the concentrated or the force that applied to a specific points in our structure. Is it clear up to this stage? Ini memang nak kena faham betul-betul sebab all the basics understanding of the finite element will be explained here. You will understand you will understand new keyword, you will understand new concept of solving engineering problem dekat sini. So kalau topik ni tak faham, topik yang lain-lain tu macam susah sikit nak faham. Macam gitu. So better understand firmly in this topics lah. Kalau tak faham boleh tanya terus. So actually, if we are able to understand this loading, actually we are dealing, we are able to solve this part of the kita punya system of linear equation. So kita ada apa tadi? Body force, we have traction force, and we have point load. So this F in our system of linear equation may came from these three type of sources of loads of loads. Yeah. All right. Now let's look at so kalau ingat lagi tak yang dia punya standard procedure for solving finite elements. First, we must have geometry. Once we have geometry, we need to discretize it. And then once we discretize it into smaller element, then we may look at the loading. And then once we understand the loading, apply loads. So apply loads, and then we in the first step here, we may look at the boundary condition or support conditions. And then we have to understand as well in the fifth steps here, what type of material are used in our structure. Material, maybe a single material or several type of material. And then when we have all of this, actually this must be from top to down. First we need to have geometry, we need to discretize, but from step number 3, 4 and 5, we can we do not need to follow this step from top to down. So we may this material can be in number 3, boundary number 4, loading number 5. So it can be the order is not strictly applied lah dekat sini. And then when we have all of this information, then we can start to set up the system of linear equation in the form of KQ equal to F, so that when we solve this equation, we can obtain the Q, which is refer to the displacement of the structure under the given loadings to our structure. Then from the calculated displacement, from this calculated displacement, we can obtain normal strain, then we can obtain the normal stress. So kalau ini yang you all have to understand, the flows from the geometry we discretize until we able to set up the system of linear equation, so that we can able to determine the displacement first. So once we have the displacement, then we can obtain the normal strain and also normal stress. Okay. boleh follow setakat ni? Yang ni dia punya ni kita akan guna pakai dia sampai habis semester. Alright, but let's say we have geometry, but how can we discretize it? Okay, that's the question. So let's say this is our geometry yang kita ada dekat sini ni, which is dia cakap kat sini, consider a non-uniform bar subject to a general loading condition as shown. So kita ada bar yang tak uniform. That means the size of the bar is not uniform. So that means it may have larger diameter on the top, and then smaller geometry or diameter at the bottom or at the tips. And then dia punya section dia ni, dia varies kan, dia tak sama. So how can we discretize? Discretize ni maksudnya kita subdivide our structure, the whole structure into several small elements. How small or how big the elements? You engineer have to decide how small you want to use, how big. But in this course, usually we will instruct you to use how many elements to simplify the problems. So the process of subdividing our geometry into smaller elements is known as discretization process, and the element itself, the small element that we have is usually called as a mesh. Alright. So kita dah ada geometri tadi, then kita kena discretizekan dia. Ini kan dia punya flow tadi tu. Ni kita dah ada geometri, dah ada. So kita geometri, the physical geometry. Ini maksudnya physical geometry. And then we have to discretize. So how should we discretize our geometry? So in this case, it's mentioned here, the bar that we have, the non-uniform bar, is discretized into 4 section. Maksudnya 4 section dekat sini, kalau kita tengok, this is the first section, second section, third and the fourth section. Tapi, okay, this word is very important. Each section has uniform cross-sectional area. So daripada non-uniform bar, kita pecahkan dia kepada 4 elemen in this example, and each of these small element must have uniform cross-sectional area. So macam mana kita nak buat tu? Kan? So sebagai contoh, kalau kita belajar integration, so I have, let's say, mana saya punya ni? Okay, let's say this is my structure, which is dia tak uniform kan? Okay, dia macam gitu. So how can we make these structures, or in terms of integrations lah, to make it the prediction is much more accurate. Sebagai contoh, this is my structure, which is kita ada area dia, kan? Dia ada area dia ni. Okay, area. Saya tulis dengan yang hitam lah untuk original physical geometry. So kalau saya nak diskretaskan dia kepada bar ataupun section with uniform cross section, so it can be something like this. We can take this point as our reference, then we project it straight downward. So this is our new element, which has uniform cross section. But whether our new section here will represent the physical one, kan? Dia tak sama. Kalau tengok area of the red element is not equal. It's bigger than the one that I drawn using the black line, right? So yang ni kita tak boleh pakai because it's not representing the physical one. Sebabnya size dia lagi besar. Sebab apa? Sebab kita use this reference as our reference, the 2 point as our reference to do the projections in order to get uniform cross-sectional area. The second one, let's say if I take the point here and then I project it upward, then saya akan dapat uniform bar juga, kan? Tapi the area of the ni yang the green area ni much smaller than the black area one. Sebab dekat sini ni we lost this part, right? And the other side as well. So this approach cannot be used as well. So the best way, if we have non-uniform structure like this, to obtain equivalent or approximately equivalent area, what we can do is we take the mid section between the top line and the bottom line. So kita akan ada somewhere dekat sini. And then from there, we take this point here and then project it to the top and project it to the down. That's maybe project it upward and downward. So kalau kita tengok, we lost somewhere there, but we add somewhere there. We lost somewhere there, we add somewhere there. So we expect by using the midpoint approach ni, our area will be approximately equal to the physical geometry. So biasanya untuk dapatkan area yang lebih tepat dengan physical geometry untuk non ataupun curve shape ni, kita akan pakai midpoint punya approach lah. So kalau tengok dalam these figures dekat sini pun, if you look closely, this is where the separating point that we use in order to generate the uniform cross sectional area of kita punya elements lah. So kita ada element number 1, element number 2, kita panggil dia element number 3 and element number 4. So from there, now we can kita dah boleh lupakan. Okay, kita boleh lupakan dah the physical geometry kita tadi tu, sebab dia dah digantikan oleh element that has a uniform cross-sectional area of approximately equivalence in terms of dia punya area dengan the physical geometry. So daripada kalau tengok dia punya progress daripada non-uniform bar yang physical tadi tu, kita pecahkan dia kepada 4 section untuk this example. Kita boleh pecahkan dia kepada lebih banyak segmen, and then we substitute it with the uniform bar element, and then later on actually we can further simplify kan dia into just a line element macam gini je. Tapi kalau saya boleh draw macam gini, kat sini kita ada point, sini point number 1 kan, ni point number 1, this is point number 2, and then somewhere there we have point number 3, we have point number 4, which is point ni adalah, kalau kita ingat yang baru ni kan, elemen dia bersambung di antara nodal point kan, dia bersambung pada nodal point. So this 1, 2, 3 ni adalah kita punya nodal point lah. This is point number 4 and point number 5. Considering kita punya x direction is positive downward. So this is the positive x directions. And then ayam saya dah bunyi. Yeah. Alright. So this is in terms of how we can represent our physical geometry into the finite element punya models. This is adalah physical geometry. And then this is a bar element. And then this is, we can call it as the finite element model. So kalau dalam kamu punya problem nanti, kamu diminta untuk sketch bar element of the structure. So lukis macam gini lah. Kalau dia minta kamu lukis finite element model of the structure, kamu boleh lukis macam gini. Kalau macam gini kita dah faham. Okay, this is, we are working with bar. So this is the element, this is our structure which is represented by finite element model. Tapi kita tak tulis lagi ni. Ni kita ada this one ni. This is how we try to differentiate between the point dengan element. So di antara node 1 dengan node 2 ni kita ada satu line ni kan. So this line actually represent the whole sections of our elements, which is this line ni it contains information of your structure ni lah, yang physical ni. Dia ada area dia, dia ada length dia, dia ada material properties dia, modulus of elasticity dia. So dia store dalam ni. Kita simpan dia dalam tu. So we have to model it something like this. Element number 2, element number 3 and element number 4. So this is how we can convert or sketch or draw our physical geometry or physical structure
Manisnya
into
kenangan.
bar elements or finite elements models. All right. So now we look at the numbering scheme. Okay, numbering scheme saya dah discuss tadi dekat sini. Sorry. So kita dah discuss. So because why we need to consider this numbering scheme? Why? Because we are actually we are working with finite element. Finite element is just the mathematics. And then we need to use computer to solve this iterative process. Actually, benda nak solve tu sama je, tapi kita apply kepada 4 elemen. So kita kena macam kita kena repeat benda yang sama kepada 4 elemen. Then this repetitive process, computer is much more efficient in doing this kind of process. Tapi komputer kalau kita tak bagi tahu ni node nombor 1, ni node nombor 2, ni elemen nombor 1, komputer dia tak faham, dia tak boleh nak solve. So we have engineer, human have to tell the computer. So this is element number 1, element number 2, element number 3. Element number 1 ni is connected bersambung di antara sebagai contohlah dekat sini ni. Elemen nombor 1 ni dia bersambung di antara node 1 dengan node 2. Kita kena bagi tahu komputer. Kalau kita tak bagi tahu, komputer tu dia tak reti nak solve. So that's why we have the numbering scheme here. So numbering scheme is not only applied to the nodes numbering and also the element numbering. It also applied to the force. Actually, on each nodal points, actually you can label all the what we call it a variable for the displacement. Usually we use q. At point number 1, you can label q1. At point number 2, we can label it as a q2 for the displacement. And then for the force as well, in fact, we can label F1, F2 until Fn, depend on how many number of nodes that we have. So let's say we have 5 nodes here. The biggest F we have F5. So this is refers to the point load. If we write the force something like this, but it's not necessarily the force will be applied at each point dekat sini. Maybe the force will be applied dekat sini je. So when only one force applied at one node, so only F5 yang ada value, and let's say 1 kilonewton. You can label F1, F2, tapi their value is just 0 lah in this case. But you have to understand how we label the element. We label the nodes to our structure. Usually, the number start according to the directions of our axis lah. Let's say this is the start of our structure dekat sini, and then our x is in the right direction. So the numbers, so kita boleh jadikan kat sini kita punya origins of our x coordinate, and the same for the nodes numberings lah. So nodes number 1 will begin to the most left end of our structure, then increase in its number towards to the other end of our structures. Ada soalan tak setakat ni? Kalau ada boleh tanya.
That's it.
Ya?
Setakat ni yang pasal labeling tu kita tak masukkan sekali dia punya body force ke traction force ke.
Um, dia akan ada dekat situ sebenarnya. Macam dekat sini lah. Macam yang saya explain just now tadi tu, sebentar tadi. Force traction force nanti dia akan apply kepada nodal point tu. So kalau ada traction force, kalau ada body force, dia akan apply kepada nodal point. Nanti kita tengok macam mana kita nak dealing dengan traction force dengan body force. Sebab kalau kita tengok macam gini, macam dia apply pada point load saja kan, point load. Tapi untuk body force actually we have to convert body force and also the traction force into the equivalence point load. Kita kita kena convertkan dia. Itu ada part nanti. Tapi untuk menjawab soalan tadi, body force dengan traction force kita akan masukkan bersama dalam apa ni? Dalam F ni lah. Cuma dia ada certain approach untuk dealing dengan these two type of forces tadi tu. Okey, boleh saya menjawab soalan ke?
Boleh saya?
Alright. So we go step by step. Nanti kita akan sampai yang kat situ tadi. Alright. Now once we understand the numbering of our element, kita dah tahu elemen kita tadi tu is connected from nodes number 1, nodes number 2. Kita ada 5 nodes tadi kan, 3, 4 dengan 5. And then in term of the elements numbering, so this is element number 1 ni element number 1, element number 2, element number 3 and element number 4. So maksud dia kat sini, when we have this, we have to establish the element connectivity between these the elements. Sebab komputer dia nak tahu ni, elemen nombor 2 ni dia bersambung dengan elemen mana ni, kan? Kalau dia bersambung pada node yang mana. So in this case we have to come up with this kind of table where we have the list of element. Kita ada E ni elemen dengan nodes. Nodes kita ada two terms kat sini, local number dengan global number. Global number ni maksudnya kalau kita tengok dia secara keseluruhan kan, kita tengok dia secara keseluruhan ni, kita akan nampak 1, 2, 3, 4, 5 kan, kita nampak kesemua sekali. Tapi kalau kita tengok secara lokal, saya nak tengok sebagai contoh elemen ni sahaja. So untuk elemen ni dia ada berapa nodes? Dia ada 2 je nodes. Kan, which is kita boleh ambil ni, this is as a node number 1 and this is as a node number 2. Let's say kalau saya tengok locally lagi untuk elemen yang ni, 2 and 3 ni, saya tengok dia secara lokal kan, kita pergi dekat elemen number 2, so kita tengok dekat elemen 2 je, kita tak hiraukan elemen lain. So untuk satu-satu bar elemen ni dia hanya ada 2 nodes, node 1 dengan node 2. So that's why untuk local ni kita hanya ada 1 dengan 2 ni je. Untuk merujuk kepada satu elemen tu, secara lokalnya dia ada 2 nodes saja. Tapi secara globalnya, node 1 dia bersambung di antara elemen 1 bersambung di antara node 1 dengan node 2. Untuk nodes number 2 dia bersambung di antara untuk elemen number 2 dia bersambung di antara
Node
node 2
2,
dengan node
3.
3. Elemen number 3 bersambung di antara 3 dengan 4 dan seterusnya lah. Kalau ada panjang lagi lah dia punya list dia. So yang ni untuk one di bar problem, benda ni kita kena listkan, tapi dia punya signifikan dia tu bila kita nak solve secara manual tu kita tak nampak sangat lah dia punya significance. Tapi kalau kita nak programkan finite element tu, we must tell the computer how each element is connected between each others. Tapi dalam topik yang seterusnya, element connectivity is very very important. Itu nanti kita akan tengok. Alright, okay, next. Ataupun okay, we take a rest dulu about 5 minutes, 10 18, 10, 20 macam gitu lah. Kita sambung semula. Boleh? We take a rest dalam 5-8 minit lah.
Boleh, sir.
Alright. Mungkin nak solat sempat kot. Ada siapa nak solat dulu ke, nak minum dulu. Alright, 10, 20.